Let's just wait for a couple of more minutes and then we'll start. Hello everyone, I'm Tanya. I'm one of the tutors, TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. So today we'll go over the questions of week 4 and just go over some questions that will help you solve the week 5 assignment. Okay, so let's begin. Okay, before that, just a summary of what you had studied and what would help you solve the questions. So delta E trim or delta E required to trim the aircraft at a given CL is what is given in the first equation. So we know that it has an intercept. So it has an intercept CM naught by CM delta E with a negative sign. So since CM naught is positive and CM delta E is negative, the overall intercept is positive. Similarly, in this case, the numerator is positive, denominator is negative. So your slope is negative. Okay. So why is CM naught positive? I've asked this multiple times. So I'm just going to go over it so you have no doubts over that point. Why is CM naught positive? Can someone tell me why CM naught is positive? Put it up on the chat box if you don't want to speak up. Am I audible? I forgot to ask you, am I audible? Someone just confirm if you can hear me. Am I audible? Yes. Okay. Thank you. So can anyone tell me why CM naught is positive and why CM delta E is negative for that matter? Let's start with CM naught. Why is CM naught positive? I think we discussed this extensively in each of the previous recordings, each of the previous lectures. So I had obviously mentioned it in the first two weeks, and we had discussed this in every one of these weekly lectures. Do you agree with me that CM naught is positive? And if yes, if not, please do tell me why. Can someone tell me anything they know about CM naught? Did you all look at the lectures, the previous lectures that sir had uploaded, and have you attempted the questions? Have you attempted the assignments? We had discussed this and I had gotten correct responses the last 2-3 times. Can someone just tell me anything they know about CM naught? CM naught, this numerator, this one. Okay, if not, please do Google it and tell me. I don't think there is a point in proceeding if CM naught is not clear, because that is, I think we had discussed this in the very first lecture, and it's one of the first variables that we had looked into. What is CM naught? Please Google and let me know. Just put it up on the chat box. Anything that you find out about CM naught, whether you agree with it, don't agree with it, any justification, or if you want me to explain it again, which I don't think is necessary. But please, someone please tell me something about CM naught. Or any one of those terms in that first equation, if you can tell me something about it. Just put it up on the chat box. Is my question clear? Do you know what you're supposed to tell me? Like, is my question clear? CM naught is a moment with zero deflection of elevator. All right. Okay. Okay. So if we don't take elevator into consideration, what is CM naught? Just from the pure stability aspect. You are right. It is the moment with zero deflection of elevator. But other than that, so the stability graph is CM versus alpha, right? So it's pitching moment versus alpha. How should the graph look? Positive, negative intercept, or positive, negative slope? The two parameters we need to describe a graph: slope and intercept. Negative slope, correct. And intercept? Negative slope is right, which is what is required for a stable aircraft. The only criteria, in fact, for a stable aircraft is that it should be negative. Yes, intercept should be positive. So the graph looks, oops, just a minute. Yeah. So the graph looks something like this, with a positive intercept CM naught and the slope CM alpha. So why is the intercept positive? Or why do we want it to be positive? Positive stability. So the only condition for stability that I have been saying repeatedly is that for static stability, longitudinal case, you need Cm alpha to be less than 0. This is the only condition for stability, right? You just need the slope to be 0. Yes, yes. That is the only condition for static stability. Nothing else affects the static stability. Cm alpha needs to be negative. Why should, my question is Cm naught, it's regarding Cm naught. Should it be positive, negative, 0? Since you've told me that it's positive and it is positive, do let me know why you think it is positive, not why you think. It has been dealt with in all of the lectures. So tell me why Cm naught should be positive. It has nothing to do with stability. Let me give you a hint, something regarding trim. What is trim? What is trim? What is trim? Inherent property of the airfoil or the plane to nose forward. I'm not sure what that means. Inherent property of the airfoil or plane to nose forward. I'm not sure I understand that. What is trim? Trim is the Cm not being positive has something to do with trim. What is trim? Cm is positive when the plane moment is anti-clockwise. Yes, nose up is positive, yes. But where is Cm not there? Why do we need Cm not to be positive? Cm is positive even here, Cm is positive even here, right? So why is Cm not? Why is the intercept positive? Why can't the graph be something like this? Here also it's a stable aircraft because negative slope. To trim at positive angle of attack, finally. Trim is a condition where Cm is 0 at some angle of attack, exactly. And you need Cm naught to be positive to trim at a positive angle of attack. I'm going to keep asking this in every class till it's clear. Cm naught is desirable to be positive so that you trim your aircraft at a positive angle of attack. If this were your graph, you would trim it here, right? That is trim. So at that angle of attack, your aircraft would trim, but that is a negative angle of attack, which is not desirable. We require it to trim at a positive angle of attack, which is why your Cm naught is desired to be positive. It has nothing to do with stability. The only condition for stability is that Cm alpha should be less than 0. The slope has to be less than 0. All right. Okay. So the conditions that we discussed, that were discussed in the previous week, there was cruise, climb, landing, and some other maneuvers. So during cruise, our condition we know is that lift equal to weight. We did all of our calculations based on this. Lift equal to weight. That was our equations of motion. For steady climb, the equation of motion is slightly modified. You have thrust minus drag minus W sine gamma. What is gamma? This gamma, it's a new symbol. What is it? For trim, it was just lift equal to weight. Now it is lift equal to W cos gamma. So what is gamma? What is this gamma? This angle gamma, small gamma. Did all of you submit the assignment, week 4 assignment? I hope you did because it was due last week. So what is gamma? the angle gamma. So according to these equations of motion, if I am to draw the free body diagram, it will be something like this, right? So it will be something like this, where weight is acting downwards. This is W. This would be drag. This would be us. Sorry, this would be lift. This would be drag, right? Something like this. And this angle is gamma. So what would gamma be? Just let me know if I'm making some mistake. If this was the free body diagram, these would be the equations of motion, right? So T minus D minus W sine gamma, yes. Lift minus W cos, yes. Yeah. So can you tell me what gamma is from this diagram? Also, just let me know if the diagram has any errors. What is gamma, cos gamma, sine gamma? What is that gamma? At least guess. No? Just guess. From the free body diagram, thrust is in this direction, so the aircraft is moving in that direction. Angle with respect to inclination. What is inclination? So it is the flight path angle. Gamma is the flight path angle or climb angle in this case. Inclination, I'm not sure, is a term that we have defined for aircrafts. So it is the flight path angle, gamma. Angle of attack with respect to free stream velocity. Angle of attack, how do you define angle of attack? We had discussed this last class again. What is AOA, angle of attack? How is alpha defined? What is alpha and how is it defined? Alpha is angle of attack. How is it defined? How is angle of attack defined? Alpha, angle of attack, how is it defined? With respect to wind flow. Yes, what with respect to wind flow? Angle has to be defined by two line segments, right? What are the two line segments? One is wind flow as in relative, yes, chord line with respect to wind flow. So, one answer that came here for gamma was angle of attack with respect to free stream velocity. That so when you define an angle, you need two line segments. Here, angle of attack with respect to free stream velocity, one is a line segment, one is already an angle. It does not make sense. So this is the flight path angle, gamma. Okay, angle of attack and flight path angle are completely different things. Angle of attack is rightly defined here as the angle between chord line and wind flow. Wind flow as in relative velocity, V infinity. Okay. Okay. So these are the equations of motion for climb. Now the equations that you used for landing are given here. Similar equations just in the reverse direction. So now while landing, due to ground effect, there is a change in the alpha, the angle of attack seen at the tail. Yes, angle of attack seen at the wing and the tail are same or different? If I use the same airfoil, so wing and tail, and if I don't have any wing setting, tail setting angle, is the angle of attack seen at the wing same as at the tail? Alpha wing, alpha tail, are they the same if all other parameters remain same? Yeah, okay. So if the angle of attack seen at the tail and angle of attack seen at the wing in an aircraft, are they the same? Okay, yeah, sure. Do you want me to type it down? So angle of attack at wing and angle of attack at tail, are they the same if every other parameter is same? Just a second. Yeah, so this is the question. Angle of attack at tail, angle of attack at wing, are they the same? Yes. Can you tell me why they are the same? Why would they be the same? No, if there is no tail setting angle, no wing setting angle, no tail setting angle, the airfoils are the same. They are the same. Okay. So we discussed this, I think, again in week 1, week 2, and repeatedly, that there is something known as downwash. There are something known as wingtip vortices, right? So when the flow on the lower surface of the wing and the upper surface of the wing interact at the tips, there is a certain vortex generation. And this vortex generation may be carried downstream. And when all of this is carried downstream, there is a downwash component that is induced at the tail, which is why the angle of attack seen at the tail is less than the angle of attack seen at the wing due to downwash. You remember there was a component epsilon equal to epsilon naught plus dou epsilon upon dou alpha into alpha. There was this epsilon, right? So downwash. This downwash is the reason that the angle of attack seen at the tail is less than the angle of attack seen at the wing. Similarly, the free stream velocity seen at the wing is different from the free stream velocity seen at the tail. In fact, the one seen at the tail is lesser because there is a downwash component. All right? Okay. So now, during landing, due to the ground effect, there's again a change in the angle of attack. This has been explained extensively in Sir's lectures. Please do go watch it again, the week 4 lectures, okay? So due to ground effect, the plane is landing, and then due to the impingement of the velocity, there is a change in the angle of attack seen at the tail, because of which the elevator with how much we need to deflect also changes, all right? Actually, elevator trim or how much elevator we require for a given CL trim was given by this equation. But because there's a change in the angle of attack at the tail, the delta E required to trim the aircraft also changes, right? To counter the nose down effect. Okay. Then the two conditions discussed in the lectures was the minimum thrust required condition and the maximum power available condition. So these are just some terms that you will require while solving the questions. So in minimum thrust required, you have L by D max. Okay. So you remember that equation, thrust equal to, for cruise, it was thrust equal to drag, lift equal to weight. If you simplify this, you know that if it is minimum thrust, your L by D has to be maximum. Okay. Similarly, when you solve this L equal to weight equation, you get this. Okay. Now for the power available case, the conditions slightly change. So you have maximum power available. Maximum power available is what? This thrust into velocity is power available. And this drag into velocity is power required. So the point at which you have maximum power available is your maximum rate of climb. Okay. These were some conditions discussed in the lectures. Okay. Now, some maneuvers that Sir had discussed was pull up and steady coordinated turn. In pull up and steady coordinated turn, your lift is not equal to weight. So there is a load factor N. N is nothing but lift upon weight. For a cruise, how much is the load factor? Cruise load factor. For cruise, what is the load factor? What is the load factor for cruise? Load factor is this N, okay? N. It's defined by lift upon weight. For cruise, what is the load factor? What is the load factor for cruise? Just look at the equations that are given to you. It's right here. So now you can tell me what is the load factor for cruise condition. Lift equal to weight. So what is the load factor? Exactly. So 1 is lift upon weight is 1. Okay. So for pull up and steady coordinated turn, you have other factors coming into play. So lift is greater than weight. Pull up, most certainly, right? You need more lift to counter the weight to finally take off or pull up. So obviously lift is more than weight. For steady coordinated turn, there is an angle phi. So that produces the component and your lift is not equal to weight. Okay. So when you solve these two sets of equations, you get two Q conditions. Q is what? What is this Q? Q. So when you solve these equations, you can see that Q is defined as here. Just look at this from here to here. If you see what is Q, it's V upon R. Yes. Just let me know if I'm making any mistake, okay? So it is V upon R. So what do you think Q is? Moment of deflection required for changing direction. Q is the pitch rate. Yes. I think if you just combine both of your answers and try to rephrase it, yes, Q is the pitch rate. Okay. Yes. Okay. So now when you see, it's just a empirical relation, this 1.1, it's just approximation. So delta E, the amount of change of delta, the deflection in elevator required is related to this Q. Okay, Q is different for pull up and for steady coordinated turn, and for other maneuvers, it's different. Okay, so Q keeps changing. If you plug that value in here, you will know how much you need to change your delta E. Delta E trim is calculated from this equation. But now we saw in the previous slide that there is also an additional delta E term that is required to be added because of these maneuvers. Okay, so that is added to your delta E trim required. Okay, so this needs to be taken into consideration when you see, suppose you can deflect your elevator maximum 25. You also need to check this condition, right? So this delta E also should be accounted for. Okay, delta E. Okay. Now I think let's go with the questions. Yes. For steady coordinated turn, pitch rate Q is given by. It was there in the previous slide. Just try to recall. So just see here, pitch rate. Q is the pitch rate. Steady coordinated turn is one of the maneuvers, the one with the angle like W cos phi equal to L. That is steady coordinated turn. What was the pitch rate? I think it was given in slightly different terms, but if you simplify it, you should get one of the options here. What was the pitch rate for steady coordinated turn? Option 1. Okay. So let's just look at the thing. It says G by V N minus 1 by L. So it is G by V N minus 1 by N. Now, you simplify this, you get G by V N square minus 1 by N, which yes, is option number 1. Correct. Okay, let's go to the next question. For a steady climb, which of the following is correct? CL climb is greater than cruise. CL climb is equal to cruise. CL climb is less than cruise, or none of these. CL is coefficient of lift. Is it less, more, or equal? for climb. So for cruise, you had lift equal to weight. For climb, you had, what was the equation? Lift equal to W cos gamma, right? Now look at these two questions, equations and try to tell me. Just look at those two equations. This is for cruise. The first one. Okay, I'm sorry about this. Yeah. So first one is for cruise. This is for climb. Now tell me, if lift is given to you, how do you find out a CL? What is the equation for CL? What is the equation? Option 3. Can you justify your answer? So Haril says option 3. Can you justify that answer? Yes. What is the lift equation? How do I find out CL? What is the equation? So lift is half rho v square SCL. Now just plug in these two and you should be able to see that CL climb is always less than CL cruise, right? Because there is a cos gamma term there. Correct? Flight path angle is never almost 90 degrees. It's always less than 90 degrees. So always your CL climb will be less than your CL cruise. Right? Option number 3 is right. Does anyone have any questions? Yes, that is the correct equation, Vamshi. That is right. So if I just use the two lift terms here and substitute it into finding CL, you will see that CL climb is always less than CL cruise. Correct? Yes. Okay, let's move on to the next question. Okay. So they've given you some data to be used for two questions. They've given you VH. What is VH? They've given you VH, eta T, tau, CL alpha T. So what is VH? Let's go over each of those terms. Let's see what they are called. What is VH? What is VH? What is VH? Tail volume coefficient. No, no. What is tail volume coefficient? Yes, I. Okay. It's the horizontal tail volume ratio. Okay. So I'm going to give that. So yeah, okay, fine. So VH is ST upon STLT upon SC bar. Okay, where ST is tail area, S is wing area, LT is the tail moment arm, C bar is the mean aerodynamic chord. Okay, yeah, so it is called horizontal tail volume ratio. Volume coefficient is fine, it's correct. Okay, eta T, eta tail, what is this? What is eta tail? Eta T. What is eta tail? Eta is usually something to do with efficiency. Yes. Mostly that's where we use it. So what is eta tail? It is a tail efficiency factor. So can you tell me what it means, or what is the equation? What is eta tail? Eta tail is equal to what? Why does it come into place? It's the tail efficiency factor. Of assignment 6, we are still doing assignment 4 questions. We'll discuss assignment. Ratio of dynamic pressure at wing to that of tail. Yes, so it's yeah. So what changes there is just the velocity. So it is the V tail and V infinity square. So this is what is tail efficiency factor? Dynamic pressure. Yes, correct. Now what is tau? Also, you'd asked something regarding assignment 6. We'll discuss that maybe week 6 or assignment 6, I think week 7. If you have any questions regarding those assignments or the options, please to put it up on the forum so that the other TAs can respond. But discussion of the answers will only be after the assignment is submitted. Okay, yeah. So now let's get back to what is tau. This term, tau. What is tau? What is tau? The control surface effectiveness parameter. In this case, it's elevator. So elevator effectiveness parameter. Okay. That is tau. Okay. What is CL alpha T? This last term, CL alpha tail. What is CL alpha tail? CL alpha, you know, CL alpha of the tail. So what is CL alpha? What is CL alpha? Isn't it the slope of the lift curve slope? Lift curve, lift versus alpha graph. This is the lift curve slope, and that slope is CL alpha. Yes. Okay, so the lift curve slope of the tail is CL alpha T. Now let's find out CM delta E. What was CM delta E? What is CM delta E? What have they asked you to find out? CM delta E. How do you find that? What is CM delta E and how do you find CM delta E? CM due to deflection in elevator. Correct. Perfect. So how do you find that? What is the formula? So the formula is this. This is the formula. All of these terms are given directly to you in the question. Can you just substitute it quickly and tell me the answer? CM delta E. And CM delta E will always be negative. Okay, so this is my tail, and this is my fuselage reference line. So if I deflect the elevator down, elevator deflection downwards is considered positive. So you have an increase in lift, right? And this increase in lift will create a nose down moment at the CG. You will have a delta M, which is nose down. Nose down is negative CM, negative pitching moment, okay? Pitch up is positive, pitch down is negative. So positive delta E gives you negative CM. Therefore, CM delta E is negative. Okay. Can you just tell me the value quickly? Just substitute all the terms are given directly to you in the question. Just substitute and tell me. What is the answer? Just all of these terms are given to you in the question. Just plug it in and tell me. Let's try to solve it. Minus beta is 0.85, BH is 0.48, C alpha is 4.634, and tau is 0.46. How much is it? 0.869. Okay, thank you. 0.869. Okay, negative. Yeah. Okay, next question. Using the same details in the previous question, what is the delta E required to trim the aircraft with a static margin of 12%, CL trim 0.27, delta E naught 0.049 radians? They've given you the equation directly. So can you solve it? Can you solve this? Delta E required. Delta E naught is given to you directly, 0.049 minus, what is DCM upon DCL? Denominator, you just found out. It's 69. What is the numerator? CL trim is 0.27. So what is DCM upon DCL? What is the numerator? What other thing is given to you in the question? What is DCM upon DCL? Just try to solve this and tell me. Let's just give you a couple of minutes. Static margin, exactly. So a static margin is the negative of DCM. Okay, so static margin is minus DCM by DCL, which is X bar NP minus X bar CG. Okay. Static margin is the negative of the DCM upon DCL. Okay, so your CM versus CL graph is something like this with a negative slope. It's similar to your CM versus alpha. Okay. And the negative of the slope is static margin. So for a stable aircraft, static margin is always positive. In our case, it is 12%. When you plug it into the equation, tell me what the answer is. Here it will be minus 0.12. You can, both of you, can you not see the presentation? Khyati, can you please confirm if you can see my slides? Can you see me writing? It's visible. Okay, Vamshi, you'll have to check your connection because it is visible to the others. Okay, yeah. Yes, can you confirm if it's visible, Vamshi, or do you want me to try sharing it again? Okay, I'm just going to proceed. Can you tell me the answer to this? I've plugged in all the values here. Let me just try solving it myself. Okay, I'm getting a 0.1012 radians. I'm getting this. Okay, thank you, Amsi. That was visible. Okay, so I'm getting 0.012 radians. Let's just move on to the next question. This is just the formula I've used here. Okay. Let me know if I'm making any mistake somewhere, all right? Okay. Maneuvering point is defined as that CG location where, this is just the definition, direct definition. What is the maneuvering point? So you have XAC, you have XNP, and you have XMP, maneuvering point. So how are these defined? How is, in this question they've asked you XMP, maneuvering point. How is it defined? It's just the definition, okay? So this is d delta E upon d delta E upon delta N is 0. The point at which d delta E by dN is 0. How is the neutral point defined? What is neutral point? How is neutral point defined? How is neutral point defined? Neutral point or aerodynamic center, can you tell me how it is defined? Can you tell me how neutral point is defined or aerodynamic center? Or tell me something about them. Maneuvering point, now you know it is d delta E by dN should be 0. That is the point. Neutral point, aerodynamic center, can you tell me how they are defined? How is neutral point or aerodynamic center defined? Okay, let me tell you. So aerodynamic center is defined, pitching moment is constant. Perfect, perfect. So aerodynamic center is defined for the wing. Is a point where pitching moment is constant with respect to alpha. Now, similar point for the entire aircraft is known as neutral point. Okay, that's the only difference. All right, let's go to the next question. In a flight test, following data was obtained while trimming the airplane at different speeds. So they've given you different speeds, they've given you different angles of attack at which it was trimmed, and different elevators, different CL trims, and different CG locations. So those are your columns: alpha trim, CL trim, elevator required for trim, and CG locations. Okay, and they've given you the lift curve slope. Lift curve slope is CL alpha, and it's at per degrees. Okay, yeah. So the first question is, what is the value of the stick fixed neutral point? The difference between stick fixed and stick free will come, I think, in the next week. But as of now, what is the value of the neutral point? How will we go about doing this? I believe the solutions have been uploaded, so you should be able to see it. But let's solve this for this class. I'll give you a couple of minutes to try and come up with the process. We'll solve it together, but just let me know how to start. Given you alpha trim, CL trim, elevator required, CG location. Okay, so this is the equation with which we will begin. Can you try to solve it? At least start. If not, we'll solve it together. This is the equation that you will be using. Yeah. Okay. So they've given you 4 points. Okay, so let's just do this. Okay, so they've given you 4 points. Let's take 1, 2, 3, 4. Right? So what we do is we take the first 2 conditions and plug in those 2. Okay, first we'll take the first case. Okay, the 100 meters per second. Now, what is the delta E of the first case? It is 3 degrees up. Upward deflection is considered negative. Upward deflection of the elevator is considered negative. That is our convention. Downward deflection of the elevator is positive. Upward deflection is negative. So this is negative. This is positive. And this is positive. Okay, so for the first case, your delta E required is -3. Delta E naught, we don't know. We leave it as such. Delta E naught plus X bar NP, we don't know. Leave it as such. X bar CG is given to you is 0.32. Just a minute. Is 0.32. Okay. So I put that here. CM delta E, we don't know. We'll put that here. CL trim is given to you as 0.54. Okay, this is for the first condition. Now let's repeat for the second condition. Second condition, it says deflection of elevator is 1 degree down. Down is positive. So you have +1 equal to delta E naught plus X bar NP minus 0.32 by CM delta E into 0.35. Now we have simultaneous linear equations. How do we go about solving it? I subtract the second equation from the first. Okay, so I just do minus, minus, minus. What do I get? I get -4 equal to X bar NP minus 0.32 by CM delta E 0.54 minus 0.35. Okay. Okay. Now simplify this equation, write it down in terms of CM delta E or X bar NP or one of those 2. Okay. So I think I will just write it in terms of, let's see, we'll write it in terms of CM delta E. So CM delta E is, this comes to 0.19, so it comes minus 0.19 by 4 X bar NP plus 0.32 into 0.19 by 4. This is 0.19. Okay, this is 0.19. All right. Is this first equation clear to you? The CM delta E. Till here it's clear? I just took the first case, I put it in the equation. Second case, put it in the equation, and then solve the simultaneous linear equations in terms of CM delta E, X bar NP. Wrote the equation in terms of CM delta E. That's all. Okay. Now I repeat for the next 2 cases, for third and fourth. So I take 0. 0 doesn't matter, so up or down. You have again delta E naught, we do not know. X bar NP minus 0.44. CG location has shifted. CM delta E, again, we don't know. And this is 0.43. Here you have 1.5 down. 1.5 down is positive or negative? I've written it there, it's positive. So 1.5 is delta E naught plus X bar NP minus 0.44 by CM delta E. This is 0.14. Again, subtract the second equation from the first one. What do you get? You get minus 1.5 equal to X bar NP minus 0.44 by CM delta E into 0.43 minus 0.14. Okay. Again, repeat the same thing that we did for the first case. Write the equation in terms of CM delta E. So I'll just write it here. Make this. Okay. So CM delta E equals So in this case, you have 0.43 minus, okay, so you have minus 0.29 upon 1.5 x bar NP, and then you have plus 0.44 into 0.29 by 1.5. All right. So this is the second CM delta E. Now equate the two CM delta E's. These two equations in the boxes, just equate them. So what do you get? You have minus 0.19 by 4 x bar NP plus 0.32 0.19 by 4 equals minus, sorry, yes, 29 by 1.5 x bar NP plus 0.44 0.29 by 1.5. So now it's a single equation in terms of x bar NP. Can you solve this and tell me how to do, what the final answer is? Just solve this. I think the solution, there was some mistake in the solution, but we should be able to get answers similar to the options. Can you just solve this and tell me? This equation has only one variable, one unknown, x bar NP. Can you solve it and tell me what is the value of x bar NP? What is the value of x bar NP? Just solve that final equation and tell me the value. So is the process clear? You take that first equation, delta E trim required equation, just put in the 4 cases and solve any 2 equations simultaneously to get the equations in terms of CM delta E x bar NP. Then you have 2 equations, 2 variables. Again, you can use your simultaneous linear equation technique and solve for x bar NP. All right. So can you just tell me what x bar NP value is? .487. I'm getting something around, I'm getting 0.479, which is almost equal to 0.48. This is the value. I don't think you get 0.487. The solution is wrong. So you get something around 0.48. Yes, that is true. Okay. Now, next question. Find the location of CG such that the aerodynamic center, sorry, in this case, the aircraft, my bad. Find the location of CG such that the AC aircraft has a static margin of 5%. Can you try doing this? Static margin. What is the static margin formula? How will you go about doing this? How will you do this? Very simple equation, static margin. Tell me how to do this. Previous question, that's your clue. Previous question, you found out your neutral point. How will we use that here? Is the previous question clear? By the way, the process, is that clear? Just stop me anytime you have any question or anytime I'm making a mistake. Stop me and then we can discuss it again. But this static margin, how will you do this? Just try doing this. XNP minus XCG, X bar NP minus X bar CG. Static margin here they've given you is 5%, so it's 0.05. X bar NP is 0.48 minus X bar CG. So what is X bar CG? What is the value? Around 0.43. Similar question, next question, static margin 10%. Just tell me this. How do you do this? Similar question. How will you do this? How will you do this question? It's very similar. It's exactly like the previous question. Only static margin has changed. What is the answer?
I think it's the first one.
Yes, it's 0.39. So it's only change here is that static margin is 0.1. Because that's the only change from the previous question. Okay. Let's go to the next question. Okay, so week 4 assignment, I think we completed with the last question. This is another question that I thought would be beneficial. So let's go over this. I don't think we've discussed this. Okay, so the aircraft total weight is 1,245 kgs. They're giving you the wing area. They're giving you center of gravity position in ratio of mean chord. So basically, they're giving you X bar CG as 0.3. And then they've given you this graph. What is this graph? It's the pitching moment versus lift coefficient, CM versus CL. Okay. So now you can see these graphs are for different elevator deflections. The first one, the green line, is for 5 degrees up. 5 degrees up means negative 5 degrees. 15 degrees up, negative 15 degrees. 5 degrees down, positive 5 degrees. And 10 degrees down is positive 10 degrees. Okay. So let's look at the questions. How do you find the stick fixed neutral point? Again, stick fixed, stick free, I don't think we've dealt with as of now. So let's just call it neutral point. How do you find out X bar NP? That is the question. How do you find out X bar NP? Look at the question carefully. Look at the graph given to you. How do you find out stick fixed neutral point, X bar NP? This graph is CM versus CL. How do you find it? So you have your static margin is minus DCM, DCL is X bar NP minus X bar CG. Now X bar CG, they've given you 0.3. You need to find out X bar NP, DCM upon DCL. How will you find that? That is basically the graph that's given to you. For all of these lines, the slope is same because remember that we had said deflection of the elevator does not change the slope. It merely moves the line, shifts the line upward and downward. What happens is that the intercept changes. The slope remains same. So pick any line, find out the slope, you get DCM upon DCL. Can you do this question now? Right? So pick any line, take the slope. It's DCM upon DCL. Plug that in this equation, then you can find out your X bar NP because X bar CG, they've given to you in the question as 0.3. Take any line, find the slope. Take any line, take any 2 points, you can find the slope. I would suggest that you take the first and the last point so it's easier to find the values. but you can take any line, any 2 points, find the slope. Can you do this? Before doing that, what do you have to do? You need to identify the scale, right? You need to find the scale of at least the y-axis. How do you find the y scale? I'll just give you, I think, a couple of minutes, 5-6 minutes to try solve this. At least tell me this y scale, or just give me some idea as to how you're moving ahead with this question. So let's take this pink line, this first line, this one. Let's take this point and this point, okay? Take those 2 points and we'll find the slope. So tell me how you will proceed. First, we have to find out the scale of the y-axis. So I take, let's just take that first set. So I take minus 0.15 minus of minus 0.2. So that is this point and this point. Divided by how many divisions are there? 5. So I get 0.01. So that means that each small division is 0.01. Okay. So this entire thing would be, and you have to find out this entire thing. Yes. So your DCM upon DCL. CM minus, we're taking those 2 points, okay? So different CM. CM is 0 minus of how much is this value? You have minus 0.2 and then you add those 2 divisions there from the y scale. So you get minus 0.8, 0.18, sorry. Divided by the value here is also 0. This is 0, this is 0. Okay, let me just. Okay, so this point, both CM and CL are 0 at that point. So I've just taken 0 minus 1.2. This gives you 0.15. Is this clear? DCM upon DCL, how it became 0.15? So the CM at this point is 0. CM at this point is minus 0.18. CL at this point, okay. CL at this point is 0. CL at this point is 1.2. Correct? I plugged in those 2 values. This is the first point. This is the second point. This is the first point. This is the second point. I plugged in those 2 values and found out the slope. The slope is 0.15. Is that clear? Okay. So this slope, this value, I plug it into this equation. So you get minus, there's a minus here. Okay. So there is a minus there. So it's 0.15 equals x bar NP minus x bar CG. It's minus DCM upon DC. Yes, so this is x bar NP minus 0.3. So how much is x bar NP? What is the value? Just take the 0.3 on the other side. What is x bar NP? Simple addition. Just give you a minute to solve that. Just tell me. The question is right here. 0.15 is x bar np minus 0.3. So how much is x bar np? How much is x bar np? Just 0.45, right? So is this aircraft stable or not stable? Look at the graph or look at the XNP, XCG values. Just tell me if the aircraft is stable or not stable. The slope is negative, right? CM versus CL, which is what is required for stability. So the aircraft is stable. If you don't want to see it in that way, you can also see that your neutral point is after your CG, right? So something that I had told in the last class to remember is CAN. So your center of gravity should be ahead of aerodynamic center in the case of a wing, should be ahead of neutral point in the case of aircraft. Okay. So this aircraft is stable. Next question. So this is the formula that we use to find out. Yeah, most aft location of center of gravity will be most aft. How far can your center of gravity move? So if this is your fuselage reference line, this is CG, this is NP. And I told you CG should be ahead of NP for stability. How far can your CG move towards the tail? That is the question here. Most aft location of center of gravity. How far can it move? The most aft location. So now if your CG moves beyond neutral point, will your aircraft be stable? No, right? No. If you move beyond the CG, beyond the neutral point, your aircraft will not be stable. So the most aft location that the CG can travel is the neutral point. So it is same as neutral point. So XCG aft is same as XNP, which is in the previous question we had found out to be 0.45. So it's 0.45. Most aft location that the CG can follow is CG can go to is your neutral point. Okay. Next question. If the pilot wants to fly at a speed of 38.52 meter per second in trim condition, what will the trim lift coefficient at sea level be? I'll give you a couple of minutes to think about this, and then you can then we can try solving it together. Remember the keywords here, the trim. So they asked you for trim. They've asked you CL trim, and it is a trim condition. So what is the value? Very straightforward question. It's the lift equation, so CL trim. You just plug in the values here. It's 2 into lift by rho v square s. and since it is at trim, lift equal to weight. So you have 2W by rho V square S. So you have 2 into 1245.75 into 9.81 because here it's kgs divided by rho V square. Now rho is at sea level, so it's 1.225. V is 38.52 square. And they've given you area. Area is 17.075. So let's just calculate this and find out the answer. Can you just calculate and tell me the answer? Just wait for a couple of minutes. You can tell me the answer. It's just a straightforward lift equation. Just plug in the values and you can find out. And you must remember it's trim, so that's why your lift equal to weight. It's at sea level, so put in the appropriate density value. Velocity, trim velocity is given to you. If I plug in the values, I'm getting 0.787. That is given here. On the next question, note that it's a similar question, but they've changed the velocity. The pilot wants to fly at a speed of 34.2 meter per second in trim condition. What will the elevator deflection required to trim the aircraft be? Previous question they asked you for CL. Now they're asking you for elevator deflection. So you know your relationship between CL trim and required elevator deflection. So just try to solve it giving that. I'll give you a couple of minutes to solve that. Let me get some water. Yeah, okay. So you can just proceed just like the previous case, find out CL trim and use it in the delta E required equation. Let's try solving that. Let me try doing it. It's the same equation, so let's just do that. So I'll take CL trim equals 2 into 1245.75 into 9.81. So it's just 2 into weight divided by rho V square S. Rho is at sea level, so it's 1.225 velocity for trim is 34.2. It's different from the previous case. So it's 34.2 square. And S is given to you in the question as 17.075. Okay. So now let's just plug in all of these values and try to find out the answer. Let me try doing it. Do let me know if I'm going wrong somewhere. Just plug in the values and tell me. 2, 1, 2, 4, 5.75. 9.8. Remember that the weight is given in kg, so you have to multiply 9.81 divided by 1.225. It is given sea level. Yeah, so it's given sea level is given the question, which is why your density is 1.225 divided by 34.2 squared. 17.075. Okay. So I'm getting 0.999. Okay. They've asked you how much elevator deflection is required. So the equation for elevator deflection was, before that, delta E into CL trim, where delta E naught, okay, let me erase that. That was CM naught. CM naught by CM delta E. Now we do not have CM delta E in all of these. So what do? You plug it into, you have the equation, you have the line given to you as it is. So what do? You know that your DCM by DCL is 0.15, right? So you take those 2 points. You need to find out your intercept. What changes for elevator deflection is the intercept. Intercept is CM naught. So you take it at points at the trim and the CM naught points. Okay. So at trim, DCM upon DCL. At trim, CM is 0. At the other point, it is CM naught. At trim, CL is CL trim. At CM naught, CL is 0. Okay. At the two extremes. Now I plug this in. You have 0 minus CM naught. CL trim is 0.999 minus 0. What you get here is that CM naught is 0.15. Now look at these lines and see where your CM naught is going to 0.15. You have 5 lines over there. So which of these lines does CM naught go to 0.15? Right, first one. The first one, CM naught is the value, the intercept here. Erase that. So this is CM naught, this is CM naught, this is CM naught, this is CM naught, this is CM naught. For our case, we've got CM naught to be 0.15. So that happens at this red line. Now, red line in our graph is 15 degrees up. So delta E is 15 degrees up. Up is negative. So it is 15 degrees upward deflection. So that is our answer. Now let's go to the next case, next question. If suddenly a weight of 15 kg payload is dropped in flight and pilot wants to fly at same trim speed, that is 34.2 meter per second in trim condition, the elevator deflection requirement as compared to the previous case will be more, less, remain same. Let's try doing this. Follow the same process. CL trim is the same. Only thing that changed is the weight. Okay, so I'll just write that down. CL trim is not the same. Velocity at which you need to trim is the same. Just plug in the same values into the equation. Find out your new CL trim. Follow the same process. So you have CL trim as Q into W. Now you have 1245 minus 15 kgs. Okay, just give me a minute. I'll just get some water. Yeah, okay, let's proceed with this. So you have 2 into W. So W now is 1230.75 into 9.81. Our density is the same. Every other parameter is the same. 34.2 squared into 17.075. Let me calculate this. So I'm getting 0.987. Okay. Similar process, the previous case, I take DCM upon DCL. This value we already know is 0.15 minus 0.15. So again, I take at trim and at CM naught. Okay. So 0 minus CM naught. Lift at trim is CL trim, which is your 0.987 minus 0. So the CM naught I get here is 0.148, which is less than the previous case. Previous case we got 0.15. So this is 0.148 is somewhere here. So it's less. CM naught has decreased. What it also means is that your elevator deflection will reduce. Okay, so the final answer is less as compared to the previous case. Okay, now let's go to the next. Yeah, okay, so now it's just a revision of week 5 contents. So directional and lateral stability. So we begin with some conventions. The convention for directional stability is that right wing back. So right wing moving back is considered the positive yawing moment. So if your aircraft is something like this, now it moves back. Something like this. This is considered positive yawing moment. So your yaw axis, Z axis is towards the ground. Put your thumb along the yaw axis. The direction your fingers curl is the positive yawing. So your right wing back is considered positive yawing. Now relative velocity on the right is considered positive side slip angle. So if this is your aircraft and if your relative velocity V infinity, this is beta, this is considered positive beta. Okay, this is negative beta, this is positive beta. Okay, if your relative velocity or V infinity is on your right, it is considered positive side slip angle. Now, rudder deflection, convention of the control surface deflection. If I deflect my rudder to the left, so if I deflect, rudder is on the vertical tail, right? So if I deflect my rudder to the left, what happens is that it produces the camber in this direction. It gives you an extra force, delta Fy, in the positive y-axis, which produces, if this is your CG, it gives you a negative yawing moment, okay? Or it yaws your aircraft towards the left. So deflection of elevator towards the left yaws the aircraft towards left, and this is considered the positive rudder deflection, although it gives you a negative moment, okay? Now for static directional stability, what do we need? When the aircraft is encountered with a positive gust beta, you require your aircraft to align to the beta so that there is no beta angle to negate the beta. So when there's a positive beta, you require your aircraft to yaw towards the right, or you need to have negative yawing moment, correct? Negative yawing moment. If your aircraft is in this direction, it encounters positive beta, it has to yaw towards right, which is negative yawing, or which is positive yawing moment. Okay, so it gives you a positive, you require a positive yawing moment to counteract the induced beta. So your Cn beta, which is dCn by d beta, should be greater than 0, because for positive beta, you require positive n. N is the moment in the yawing direction. Okay, C and beta should be positive. Now, like I had said, induced positive beta, when there is a positive beta angle here, it's like the angle of attack. So what you have is a negative force being generated, Fy. So Cy beta is negative. Cy is dcy by d beta. Positive beta produces negative force, so Cy beta is negative. Okay. But for stability, you need Cn beta to be positive, which is why you have introduced a negative sign here. Your Cy beta is negative, but you require your Cn beta to be positive, which is why you've introduced a negative sign here. Okay, do not get confused. Okay, so what are the components that contribute towards positive stability in the directional case? Vertical tail gives you this required Cn beta to be positive. What also gives you a positive Cn beta is a swept wing. Okay, why these things give these stability is discussed in the lecture. Vertical tail, I think, is pretty obvious, because just now we saw that gives a restoring moment. Okay, so it produces a beta. So this positive beta produces a negative Fy, which gives you a restoring moment. It negates the effect of beta. It gives you a restoring moment. Okay, this is positive n. Moment in this direction is n. Okay. Now, just a comparison between the longitudinal and directional case, this table is given here. For static longitudinal stability, you require Cm alpha to be negative. In this case, you require Cn beta to be positive. The trim condition in your longitudinal case was that Cm naught should be positive to trim at positive angle of attack. For your directional case, Cn naught is usually 0 because it is, you require to be trimming your aircraft at a 0 beta angle. Okay, so Cn naught is 0 and it's a symmetric effort. Okay, now control. For the control, Cm delta E required to be negative. Cm delta R requires to be negative. If you just see the rudder convention like we discussed in the first slide and it's given here, you can see that positive rudder deflection gives you a negative Cn, negative moment, which is why Cn delta R, which is dCn by d delta R, is negative. Okay, this is very similar to the longitudinal case. You have control surface effectiveness parameter tau, Cn delta R, all of these terms very similar. Okay. Next, we look into the lateral stability and control case. Conventions are right wing down is considered positive roll. So your rolling axis is along the nose. You put your thumb along that direction and roll it. So your right wing down, rolling towards the right wing down is considered positive rolling moment. All right. So how do you achieve this motion? You deflect your right aileron up, the lift of the right aileron decreases. So this is right, this is left. If I deflect my right aileron up, lift decreases. You have negative lift, not negative, it decreases. And if I deflect my left aileron down, your lift increases. Overall, you have a positive rolling motion. All right, you have positive L, rolling moment in the rolling moment is L. Okay. Now for static lateral stability, when you need a negative rolling moment, CL. With a positive gust beta, you need a restoring moment, negative restoring moment. So in this case, it is CL beta. Okay, your force Fy produced on the vertical tail should roll your aircraft back. Correct? Correct. Yeah, you need to remember this, that this only happens when the vertical tail is above. If it's below, the same force will produce a moment that does not restore beta. Okay, so remember that CL beta should be less than 0 for static lateral stability. Now the components that produce these stability is vertical tail, when the vertical tail is above, the high wing configuration, and low wing with dihedral. Okay. Okay. Let's look at a few questions. For directional static stability, we just discussed this. Cn beta should be greater than 0, less than 0, equal to 0, none of these. We just discussed this. If it encounters a positive beta, to restore its stability, what we need a positive n, that is yawing moment. For a positive beta, you need a positive n. So positive beta requires positive n. That means dCn by d beta will be greater than 0. All right? Okay. For lateral static stability, we just discussed this. dCl by d beta should be less than 0. We just discussed this. Positive beta produces negative moment, produces a negative rolling moment. All right? Did you understand that? So you have, so if this is your aircraft, a positive beta is in this direction. This is positive beta. Now you have your vertical tail, right? Vertical tail is something like this. Okay, excuse my poor drawing skills. So if this is your aircraft, this is your vertical tail. Okay, so it produces Fy force. Okay, Fy forces acting here in this negative direction, negative Fy. Now that, since it is above the CG, this is the CG, it produces a positive rolling moment, right? Produces something like this, positive rolling moment. Just try to visualize it, it's a positive rolling moment. Right? Okay. So now let's go to the next question. Sorry about this. During a flight, if the aileron is deflected with a certain positive angle, how will this affect the directional stability of an aircraft? Just like the elevator case. If I deflect the elevator, will it affect the stability in any way? No. Similarly, if I deflect any control surface in any direction, it does not affect the stability at all. Okay. So deflecting the aileron will not produce any change in the stability. For the CM alpha case, so you had CM versus CL or CM versus alpha, any of those, you had something like this. The only condition required for stability was that CM alpha should be less than 0. Right? Now, if I deflect the elevator, what happens is that if this was the original trim, it moves to this location. Correct? It just moves the intercept. So this was the original intercept, it moved it downwards. That is the only difference. Okay, so deflecting the elevator did not change the slope, hence it did not affect stability. Similarly, these are similar airfoil shapes. If I deflect the aileron down, it simply alters it moves the graph. It does not change the slope. Hence, it does not affect stability. Directional stability is not affected by the controlled surfaces. Okay, remains unchanged. Okay. Contribution of the vertical tail to directional stability depends upon vertical tail volume ratio, vertical tail efficiency factor, both vertical tail volume ratio, vertical tail efficiency factor, or none of these. What will it be? Just think about it. Just again equate it to the horizontal tail case and try to understand. So let me try to give you, so this is the equation. Now can you try to tell me the answer? Just think about it a moment. It's very similar to the longitudinal case. In that case, it's the horizontal tail. Here, it's the vertical tail. That is the major difference. Okay. So you have the tail, a vertical tail efficiency factor. So this is definitely there. And the vertical tail volume ratio, VV. So both of these parameters are there in the equation. So answer is both. It has both eta V and VV. Okay, next question. The aileron control effectiveness depends upon lift curve slope of wing, lift curve slope of vertical tail, lift curve slope of horizontal tail, none of these. Which of these surfaces is the aileron fixed on? Give it a moment, look at the questions, read it carefully, try to tell me. Which of these surfaces or which of these structures is the aileron fixed on? Is it on the vertical tail? Is it on the horizontal tail? Horizontal tail we just studied, it's the elevator. So aileron is not there, it's the elevator. Horizontal tail, as the elevator. So vertical tail, what do we have? And wing, what do we have? Control surfaces. Aileron is on the wing, right? Because the vertical tail has the rudder, the aileron is on the wing. So its effectiveness obviously depends on the lift curve slope of the wing and not on the vertical tail or the horizontal tail. So CL alpha wing, that is what defines your effectiveness of the elevator. Okay. Next question, primary control surface for adverse yaw. What is adverse yaw? I think I will discuss all of these in the next lecture. Okay, so if you have no other questions, I think we'll end this lecture here. All the very best for your assignment 5. We'll meet again next week. If there are no questions, we'll end it here. All right. What is adverse yaw? And this is probably something that we'll discuss in the next class, but what control surface would you usually use for yaw? We just discussed this in the couple of slides before. Actually, yeah, couple of slides before. Vertical tail. Vertical tail. What control surface do you have on the vertical tail? Sorry?
Hello?
Okay, I didn't get you, but what control surface do we have on the vertical tail? Okay, we'll just wait for the others to join so that we'll discuss these questions in the next class. So if there are no other questions, then I think we'll end the lecture here. So all the very best for assignment 5.
Huh?